Hello guys, and welcome to this sort of remake of a past video of mine where I will be solving the Ricci-Flow equation, well, system of equations really, for a 2D sphere. So let's get started. So what is Ricci-Flow? Ricci-Flow is basically this equation we see here, which it basically tells us that the rate of change of the metric tensor is proportional with some constant to the Ricci curvature tensor at each point. So basically, what the hell am I talking about here? So let's, since we are talking about a sphere, we have the luxury of choosing in sort of what framework and notation of differential geometry we want to work in. So basically, let's just use the classical notation for differential geometry, which basically everything just becomes matrices and functions. So we have that the time derivative of the metric tensor, which is now a matrix of u and v, matrix function, is proportional to the Gaussian curvature, which is now a function, multiplied by the metric tensor itself. So as you can see here, this is the two-dimensional sort of analog with a notation for the Ricci curvature tensor. And as I said here, this is the Gaussian curvature, k. And this already simplifies things a lot, because G is a matrix, this is a real value, this is a matrix, again. This is just a time derivative of whatever. So we already made some progress in simplifying this. So next, what is the metric tensor of a sphere? A two-dimensional sphere, the surface of the two-dimensional sphere. The metric tensor, which is in classical differential geometry, is actually referred to as the first fundamental form of the surface, is given as a matrix valued function of u and v, like so, which is basically like a diagonal matrix. Here we have r squared sine v, and here we have r squared. Basically, this is derived from the surface equation in vector notation for a sphere, which is like r squared sine theta and r squared cos theta sine phi, whatever. I don't know it by heart. I should, but I don't. Oh well. And then you take, for each one, you take the derivative with respect to u and the derivative with respect to v, and dot product them such that this is partial u dot partial u, partial v dot partial v, and these are the cross terms here. So yeah, that's basically just a loose definition of where this comes from. You could look it up, it's easy to understand. Hence, here here we also see that I have labeled r squared, the radius of this sphere, to be a function of time, which we will clear up further down the line in a few slides or so, why I have actually chose to do that. And it will make sense, I promise. And also, while we're here, the Gaussian curvature of a sphere is just 1 on r squared. Everywhere is 1 on r squared. It's constant, we have no issues on that. That's why this example is so easy, otherwise it would be very sort of challenging to solve. But as we shall see, this will make our lives very easy. So, our ansatz. So, let us start. We need to find a solution to this differential equation, being the matrix G, which is a function of u, v, and time. Now, for a sphere, as we saw in the previous slide, it's this. But we can, if r is a function of t, it could be factored out of this equation, like I did here, which would give us that our solution to this partial differential equation is actually a function of t multiplied by a function of u and v, which is, for those who maybe have seen some partial differential equations, will know that separability is a very good condition to have when solving them, because it makes everything so much easier. And we happen to have that here. Why do we have separability here? Because remember when I said up here we have constant Gaussian curvature everywhere? Given that, one should expect that under Ricci-Flow, since everywhere has the same Gaussian curvature, the manifold should change radially by the same amount, right? Because that's what the differential equation tells us. The rate of change of the metric is proportional, in our case, to a constant. Times the metric, obviously, but whatever. Now, that means that at every step of that this system takes through time, for example, at 0 seconds we start with a sphere, and then at 1 second after, we should also have a sphere, because everywhere is changing radially by the same amount. Therefore, it's just scaling the sphere, right? So, we will take our ansatz, or our educated guess, as our solution being some r squared of t, which would be the radius, times g hat of u and v, where g hat is this matrix here, which is the matrix of a unit sphere, so of radius 1 basically. So if we take this and we substitute it back into our differential equation, we have this. We have our metric tensor here and here, and this here is our Gaussian curvature, which we said is 1 on r squared, but r squared is a function of time. Now, one thing we see immediately is 1 on r squared and r squared. These can cancel each other out, and this can be differentiated with respect to time as an implicit kind of function to give us 2r r dot, and obviously these cancel, so on this side we get minus 2g. Now here we see we have 2 and 2 on both sides, so we can divide throughout by 2. We also have g and g on both sides, so we can multiply by g hat inverse, to get rid of these, and we end up with this really nice, really simple, very easy to solve, separable first order differential equation. R dot is equal to -1. And furthermore, our initial condition, rather than being like the metric tensor of some sphere with radius r0, just becomes r of 0 equals r0. And that's easy to solve. I mean, it's like A-level difficulty. So we solve this with the given initial condition, which, like I said, it's a separable first order, and we get a solution for r of t, which is the square root of the square of the initial radius minus 2t, where t is the time that has passed since we started the process of Ricci-Flow. So if we plot it out, we get something like this, where this is the initial radius here, and it goes down, down, and it actually starts to speed up the smaller it is, because this is like a parabola shifted on its side. Here it would be like a C shape, and here it would have like an infinite derivative because it's a vertical line. And also here it will meet 0, and that's a very important sort of concept, which is the extinction time, the time passed for the manifold to basically just disappear. And that time would be equal to r0 squared divided by 2, because it could be, you can see it from this thing, right? If you set this equal to 0 and solve, you square both sides, take this one here, divide 12 by 2, and you get by minus 2, I mean, sorry, divide 12 by minus 2, you get r squared on r naught squared on 2. And that's basically the extinction time. So obviously, the larger the radius of the sphere you start with, the longer it's gonna take to disappear, right? That's basically a given. It's very intuitive to understand such a result. And also this, and I'll leave this as an exercise, could be generalized for n dimensions, which is, the only difference is that you get a factor here of n minus 1 for an n-dimensional sphere, and here's the dimension. So what this tells us is that the higher the dimension, the faster the sphere goes extinct. Now obviously one would need to prove this. I'm sort of pulling it out of a hat here, but with some Google searches here and there, you might be able to sort of see how this could be true, right? Because, you know, and it would make sense, because the more directions you have for curvature to consider, the more sort of pull you would have towards the center on an intuitive kind of understanding. But yeah, I'll encourage you to maybe dig a bit into this as an exercise. So yeah, basically that's all I have to say about this, and let me know what you think of this. Give me feedback, whether you liked the way I presented this or you hated it. I originally was planning to present this like in the previous video with a sort of Khan Academy style writing, but my handwriting is terrible and it usually takes way too long to explain something, and this is much easier because I could just flip through the slides. But yeah, tell me what you think and I could maybe make improvements. So yeah, like if you liked, subscribe if you liked, and thanks for watching.